Hey, Keith, we've got this material from last year, which was sort of in one of the main lectures. And this year I want to bring it out and put it into supplementary material. There's like some really neat stuff here, but it's maybe it's a little bit supplementary. And so what it is, you know, some of the math behind the transmit aspects of ultrasound, the diffraction and Huygens principle, and then the idea that, you know, going back to that first picture on our first slide, the idea that if you have an aperture, then what you actually measure in the far field is the Fourier transform of your aperture. So here we have 2 point sources and you get a sinusoid. So those kind of concepts are in the supplementary material. It's pretty mathy, but it's some cool stuff. This is pulling in from last year's lecture. So this is just kind of introducing what we're doing here.
So this supplementary material is not to be missed, but still supplementary and totally optional.
Totally optional, but it's very cool. Hence my discussion here, calling it some math with a very cool result. Okay, so let's get into that. Okay, so the basic idea with diffraction first. Diffraction is a phenomenon that affects all types of waves and is described as the deviation of waves from their rectilinear paths that cannot be described as reflection or refraction. So in other words, it kind of in my mind goes hand in hand with Huygens' principle and Huygens' principle says that you can approximate any wavefront as a bunch of point sources, and then each point source, so in this example here, there's a slit and much of the plane wave is just stopped, but through the slit, they're sort of approximating what gets through there is 4 point sources. Each one of them is going to emit a spherical wave because you know a point source is going to emit a spherical wave. And then to approximate the whole thing, you just take each of the spherical waves, and then for every point in space, you add up each of those spherical waves. So there's going to be areas of constructive interference and areas of destructive interference. And you get this interference pattern, like we said. And so diffraction is sort of the appearance of the sound sort of going around corners, which seems kind of weird that it shouldn't do that, but it's just really simply that if you have a sum of individual points and a point is going to give you a spherical wave, then you're going to have some that kind of looks as if it goes around corners. Okay, well, if we have Huygens' principle, then we can do a simulation of all kinds of different types of transducers. So I've done that. First of all, I just wanted to show you just some very, very simple ones. This is a very simple MATLAB code. There's one element over here, and it's just a single point. If you turn that one point on, you're going to get a spherical wave coming out from that. So that makes sense. You know, I got my tuning fork. I ping the tuning fork. It goes out as a spherical wave. Now this one's really interesting. For this one, I have 5 single points. Each point is going to send out a spherical wave, and there's going to be the constructive and destructive interference. So if we play that back initially, you see each of those spherical waves coming out, and then a later point in time, later in time. And what you see also is that the initial interference pattern gives you an interference which is kind of garbagey right up there in the beginning. And then a little bit later, what you see is there's a nice area of constructive interference that seems to be very consistent in the center right there. And then next to that, there's destructive interference. So that gives you kind of the idea that how you can use multiple elements to build up a beam and how you start to get a beam. And then down here is the next thing is again is those 5 elements, but what we're going to simulate here is as if they're curved. So playing that back again, what you can see is there's a little bit of curvature to the wavefront as the wavefront comes out there. And that little bit of curvature is going to give you a nicer beam, and it's to be a little bit tighter focus. And you can see that right here at this last time point that it's a tighter focus than over here, which is a bit broader. And so that's the basic idea behind curved transducers, is that you get some focusing ability and a tighter beam. All right, well, this is just showing you basically how you can use individual points to simulate a wavefront. And so let's go on.
And where'd you make these animations, Kim? Are these from MATLAB as well, or?
Yeah, this is MATLAB. You know, not a lot of MATLAB code. It's just basically for every time point, given a speed of sound, the wave has gone a certain radius from the initial point. And then for every point in the array, you just have to sum up each of those wavefronts and say, is it within some number of cycles of the radius that it's traveled?
That's very cool.
Yeah, so pretty straightforward, and hopefully students will have a chance to work on that in the homework. So as you can see, at each time point, the pressure wave has positive and negative points, as shown over here, but it's a little awkward to talk about each individual time point and the individual high and low pressure points. So really, it makes more sense to talk about the envelope. So that's what we see on the lower picture down here is just, instead of the positive and negatives, we're just showing you the envelope. So at every point in space, we say, well, what's the maximum that went by, maximum pressure that point in space experienced. So we're just going to get the envelope. So you can see what the beam looked like for those 5 individual points. You know, this is not the most prettiest of beams because 5 points, I mean, you never have a transducer, it's just 5 points spaced far apart. You end up with these grating lobes that are huge, but it was a nice simulation to kind of, you know, because you were able to see those individual spherical waves. So just some definitions. If you have your transducer, and there's the elements of the transducer that we talked about before, and there's this is the same one that we saw. Well, actually this one's now 7 elements. It's sort of curved. What we define is that garbagey area is the near field or the Fresnel zone. And, you know, you never get good ultrasound pictures in that area. There's a good reason why on ultrasound imaging, they don't really show you the area that's right up against the transducer. I love this movie. I love the fact that the baby is sucking its thumb. It kind of reminds me that, you know, this question of like, is there continuity of personality? So if there's thumb suckers when they come out, are they thumb suckers when they're on the inside? You know, how do other,
I have no idea.
how do other personality traits manifest themselves while they're still developing inside? I don't know. Anyway, kind of fun.
I always want to be tired and wet. It must have manifested from my days in the womb.
Let's not go there. All right. So we've defined the near field or the Fresnel zone. And if we're going to look along the axis right here, and we can now define the area where the beam is nice and smooth. It's not really very garbagey. So that's the far field or the Fraunhofer zone. We can actually plot along that line, and this is what you would see for the pressure, is that it's kind of garbagey there in the beginning, and then the pressure will increase, and then it's very smooth, and then it falls off again. So this part right here where it's very well focused is the maximum, and that's called the focal distance. This is yeah, and so that's the focal distance. You can also you know, come up with an equation for that pressure along the axis. It looks something like this. This beginning part is something that you might recognize as the original pressure, and then the equation for the sinusoid. And then there's another component right here, which is just describing how the pressure comes up and then falls down again.
Is there an intuitive explanation for why the constructive interference is so garbagey in that Fresnel zone? I don't know how to say it. If there's not, you can cut this section out. I'm just wondering if I had to repeat it back.
So it is called the Fresnel zone. At least I've always heard it called that. So is there a good reason for that, why it's kind of garbagey? It just doesn't seem, you know, the individual wavefronts are sort of kind of pointing towards each other, and it's just the interference pattern. I don't really have a good explanation other just to show you how the interference pattern is really terrible.
I'll take it.
Okay, thank you. So it was kind of fun. I had fun with this in MATLAB. I was doing these nice mesh plots. So the transducer's right here. You can see the grating lobes, and then you can see that main lobe rising right there. So then I think, oh yeah, here I zoomed in on that. So this is where the transducer is. It's pointing in that direction, and then you can see the main lobe there, and see how it gets broader. You can see that in the grayscale, but I was having fun with the mesh plot. Okay, so I could draw a line across it this way, and this is what the main lobe looks like, and you see the width there, and then a little bit further back away from the focal point, you can see that the width gets a bit wider, and so it's just going to diverge. You know, there's a reason when you do ultrasound imaging that there's one part of the image which is more in focus than closer or further from the focus. And this is exactly why. It's just that the beam is the thinnest right at the focal point.
I'm actually wondering, now that you're showing me this, for an ultrasound imaging scan, do any machines actively change the focus as they're scanning through different depths?
Oh, yeah. So you have a really great question. Let me go back to the picture of the fetus here. So you see that little carrot over there? And so when you're doing ultrasound imaging, the sonographer will actually set it up with a particular depth. And that's where it's going to set the elements to be most in focus at that depth. So on transmit, you can only specify one depth. On receive, you can actually receive back where you're focusing dynamically. So you change the focusing from all points as the echoes are coming back. It's kind of a little bit beyond sort of the topic what we wanted to talk about today, but yeah, it's absolutely true. If you really were much more interested in getting better focus further down, then the sonographer just tweaks the knob and focuses further down, and then you'd see this whole line over here being more in focus.
And I don't think you could do that with a single element. I think that would have to be phased. So we'll get to that later.
That's right. Good point. Because we're still talking about single elements today. Getting ahead of ourselves.
Just so excited. Just get ahead.
All right, I missed a point here on this one. So here, one point is that the maximum intensity is where is the minimum width. And it actually does go up a little bit higher. It's a little hard to appreciate here on my plot. It seems to go off the top, but you can see that at the focus where it's the width is smaller, that it actually is higher than down here. So, and it's going to fall off with, okay. All right. So now we get to the point where I'm going to skip some math. I mean, I kind of had all these slides queued up, so I don't want anybody to feel like, oh, Kim's really scaring me right now. It's just, I'm just going to give you like a couple of key concepts here, but then get to the result right away. All right, so the key concept is that you can take any arbitrary shaped transducer, any arbitrary shaped pressure surface, any arbitrary shaped aperture. So different words for the same thing. And you can split it up into multiple different points. Each one's going to send out a spherical wave. And you can say for any point in space, you can calculate what the pressure is going to be at that point, because all you have to do is really sum up the spherical waves from each of the pressure points on the aperture. Okay, so that's what we have down here in this equation, is basically that any point in space, you can approximate that as the summation over your aperture. So this is a two-dimensional surface of the spherical waves that are emanating within each point has some particular pressure. All right, so you can probably figure out where we're going with all of this.
I can, but I happen to see the slides and I know it's those fast Fourier transforms that you're about to bust out.
That's so funny.
I wouldn't have known otherwise, probably.
Because it doesn't have to be a fast Fourier transform. We can just go with regular old slow Fourier transforms, but you're absolutely right.
Even when you ran it in MATLAB, it was so fast.
You're absolutely right, is that what we're going to see over here is that the pressure that we're going to get in this plane is going to be the Fourier transform of our aperture function. So that's exactly right. And that is just really the coolest thing, because you can take any arbitrary shape and say, well, in the far field, I can kind of know what the shape of my pressure field is going to look like. Okay, so it's basically you do these summations and you make a number of substitutions of the geometry going from spherical coordinates into Cartesian coordinates. And then you make the assumption that we're dealing with out here in the Fraunhofer zone where things are nicely behaved, not down here in the Fresnel zone where it's all garbagey. And more approximations, blah, 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 and take into account spatial frequencies. And then in the end, what we get is that the pressure out here in the far field is related to the Fourier transform of the aperture. So whatever transducer you have is going to have some aperture. So if you have something that's a nice simple shape, like a rectangle, for example, then if you've had Fourier transforms, you know that the Fourier transform of a rectangle is a sinc. And so you can say, well, I know that out here in the Fraunhofer zone, I'm going to get something that a pressure field that looks like a sinc, because that's the Fourier transform of a rectangle, if that happened to be what your transducer was.
And Kim, are you calling it well, is Fraunhofer calling it an approximation because it really only refers to the point in space that's the maximum intensity, or it just generally looks like that whole focal field?
So this is true anywhere out there in the Fraunhofer zone. Although, you know, usually we're saying, well, what does it look like at the focal zone? So it's always going to be, you know, out further out is going to be sort of scaled differently in space and amplitude, but it's going to be still kind of that same shape.
Mm-hmm.
So I had modeled the transducer as a rectangle. So what we see is going to be something that's going to be sort of sinc-like. This is a main lobe, and then there are these side lobes. They don't seem to come all the way down to zero. I'm not quite sure. I'm sure it has something to do with the resolution of my simulation, but you do see something that's sort of sinc-like. So this is what's like totally awesome. It's really neat to see real world examples of the Fourier transform. I have some more examples to show you. You ready?
Yeah, absolutely.
Because I love real world examples. Okay, so I think they're going to be queued up in just a second here. So just some few Fourier transform pairs. If you have a rectangle in space, so in other words, if your transducer is shaped like a rectangle, then the shape of the pressure field is going to look like a sinc. And a sinc, of course, is a sine x over x. So it's a sinusoid, but then it gets smaller in space. If you have, so these are the Fourier transform pairs, and oh right, yeah. So here's another Fourier transform pair is the cosine. In the cosine, the Fourier transform of the cosine is two shifted delta functions. Well, what if your transducer was two delta functions, like you had 2 point sources? Then what you would see in the far field in the Fraunhofer zone would be a cosine. And if you don't believe me, just hang on just a moment and I'm going to show you. Okay, so I've done simulations down at the bottom, and the simulations are 3 situations. One where you have a point source. If you have a point source and you Fourier transform a delta function, you're going to get a constant. And in fact, what we saw when I did the simulation was a point source is going to give us a spherical wave. We're not going to look at a plane. We're going to look at a curved plane out here, because we just didn't go far enough for this to be really planar. But when we look at a curved plane, we see it's a constant. In fact, yes, the Fourier transform of a delta function is a constant. So if we look at that curved plane, we see a constant.
But, and since we're thinking about sort of maximum pressure or at any time, it doesn't matter if we look at it curved or as a straight plane, right?
That's true. If we were just looking at the maximum pressure, it would be we could look
anywhere relative to that source, you know.
Yeah, but the reason why I wanted to bring up the curvature is so that this one made more sense. So this is the case where you have 2 point sources, 2 point sources, and the Fourier transform of that we know is a cosine. Well, what did we get when we simulated that? Well, we had 2 spherical waves, and there's going to be an interference pattern, and this is what the interference pattern looked like. And so if you look on your curved plane, then what you would see is that it goes up and down and up and down, and you actually do get a cosine. If you looked at it this way, you'd get a cosine as well, but then there'd be some obliquity term.
Oh wait, maybe I'm totally wrong, Kim, but wait, these models, do they account for, you know, sort of attenuation of the wave? And like, whereas it spreads out, the wave at any point should be weaker, right?
Yeah, no, you raise a good point. And this simulation did not take that into account. My later simulations actually did. Yeah.
Okay, because then I would be wrong about that plane versus the, you know, the curved sort of surface.
Oh,
I'm just confusing myself, I think.
Yeah, yeah. Okay, and then the last little example I have is the rectangle. So if your transducer is a rectangle, and in fact, a lot of transducers, like, I mean, you could even say that a planar transducer is a rectangle. It's actually, it's a circle. So instead of getting a sink times a sink, you get a jink. Uh, anyway, so if you Fourier transform the rectangle, you get something that's sort of sink-like. And if you say, well, what happens in the simulation? So it was set up as in one dimension to be just a line. So it's not, it was, I actually did simulate multiple point sources, but many of them, not just the 2 point sources at either end, but so many of them. So it was approximating a line, which is sort of a 1D rectangle. And then the interference pattern looks like this. So in fact, it's really bright here, and you can just sort of make out that there's the side lobes over here, and they're lower amplitude. So that's similar to what we were seeing here, is that the main lobe was really big, and then there you see the side lobes. And so that's what you're seeing over there. So this is cool because this is a real example of the Fourier transform.
Yeah, and it's really cool for me even, I mean, especially for me, because if I took two rectangles and put them at a distance, you know, that could simulate my ring that I use in lab. And even though I'm using more complicated models, I could just be doing a Fourier transform. Right, Kim?
Yeah, that's right. Okay, so in other words, whenever we have some aperture, so our transducer, we could kind of figure out what the shape of the far field is going to look like. And in fact, and that's what we saw there. So the pressure field is the Fourier transform of the aperture function. Again, it's totally awesome.